Hello, I'm Bruno Cavalar. I'm a PhD student at the University of Warwick, and today I'll be talking about algorithms and lower bounds for comparator circuits from Shrinkage. This is joint work with Zhenjian, who is also a postdoc here at the University of Warwick. So in computational complexity, we are interested in understanding the intrinsic complexity of computational problems. We want to know how much computational resources a computational task requires to be solved. And one of the main computational tasks we are interested in is the task of our decision problems, which are problems in the following form. You receive an input and you want to know if it satisfies or does not satisfy a given property. And one way of modeling decision problems is by means of Boolean functions, which are functions that receive a binary string as an input and output either 0 or 1. And one way of studying the complexity of Boolean functions is by means of circuits. So as you see in this in this picture, a circuit is a directly cyclic graph and in which the sources are labeled with inputs and the other vertices are labeled with the logical operations and are called gates. And one of the gates is singled out to be the output gate, the vertex, the only vertex that is a sink in the direct acyclic graph. And the question we ask in circuit complexity is what is the size of the smallest circuit that computes a function f? Okay, note that this is a complete model of computation in the sense that every algorithm can efficiently be represented by a circuit. This is a well-known fact in computational complexity, which implies that lower bounds for circuits also imply in the inexistence of algorithms. Okay. So the well-known problem of P versus NP is basically about the inexistence of polynomial time algorithms for the complexity class NP. So to separate P from NP, taking the information from the previous slide, it means that it suffices to show superpolynomial lower bounds on the size of circuits computing a function in NP. However, proving circular bounds in general has proved to be very hard. Indeed, superlinear lower bounds for circuits is still an open problem. The best lower bound we have for general circuits is of the order 5n. This strongly motivates the study of restricted circuit classes, in which we hope we might be more successful and we also might improve our proof techniques. The circuit model, the restricted circuit model we're going to be restricting ourselves in this talk is the model of comparator circuits. So comparator circuits are basically just Boolean circuits that only contain comparator gates. So what's a comparator gate? So each gate has exactly fan out 2. So basically the restriction we're putting on the Boolean circuit is that we're having bounded fan out. And one of the wires of the gate will compute the OR of the incoming bits, and the other wire will compute the AND of the incoming bits. Okay? And we can consider the negations to be all at the bottom of the literals. An equivalent representation of comparator circuits is by means of this drawing as a set of horizontal lines, which we call wires, and they are labeled with literals. Okay, and each gate in this representation is basically an ordered pair of wires, which is represented as an arrow in this drawing. At the tip of the arrow is the OR gate, and the bottom of the arrow is the AND gate. In this particular figure, we can see a comparator circuit with 2 inputs, 4 wires, and 4 gates, and in which the third wire computes the parity of the 2 bits. Okay. So what can comparator circuits do? As a local notation for this slide, we'll denote CC to be the class of polynomial size comparator circuits, and CC brackets S the class of problems solved by size S comparator circuits. And of course, the size of a comparator circuit is the number of comparator gates. Okay. So simulations. It's easy to see that formulas of size S can be simulated by comparator circuits of size S. Right? Formulas are exactly circuits with fan out exactly 1. So it's not hard to see that they can be simulated by comparator circuits. However, there is already a fine-grained disparity between these two models, in the sense that just by building the construction of the previous slide, we see that we can compute parity with linear-sized comparator circuits, whereas it's well known that parity requires quadratic size formulas. It has also been proved in the past that non-deterministic branching programs can be simulated by comparator circuits with only a polynomial overhead. These two simulations give us as a consequence that the complexity class of NC1, which is contained in NL, both of them are contained in the class CC. So it would be this question: what is the relationship between CC and NC? And they are conjectured to be incomparable. So NC, which is the class of polylog time parallel computation, this is conjectured to be incomparable to NC. And for the following reasons. So first, stable marriage is a problem that can be solved by comparator circuits, but we don't expect it to be in NC because all the algorithms we know for stable marriage are inherently sequential. This conjecture of incomparability is also supported by oracle separations that were recently proved by Cook, Filmus, and Lee in 2014, and also by a recent work of Robert, Pitassi, Rosman, and Cook in 2016, who showed that there exists a function in monotone NC2 which cannot be computed by monotone comparator circuits. Okay, so there is a separation in the monotone world. With regards to majority, it's still an open question. So we know that comparator circuits can compute majority with the linear number of wires and n log n gates. This is a result of Aitai, Komlos, and Zamaredi in 1983, but it's still unknown whether majority can be computed by comparator circuits of linear size. Can we prove a superlinear lower bound for majority for comparator circuits, or is a linear number of gates enough for computing majority with comparator circuits? Okay. So lower bounds for comparator circuits. So the first monotone lower bound for comparator circuits were proved 2016 by the previously mentioned paper of Robert, Pitassi, Rosman, Cook. They proved an exponential lower bound for monotone comparator circuits. However, the first lower bound for non-monotone comparator circuits were shown also only in 2019 by Enagel and Robert. This is over 30 years. After over 30 years of study of this class, is the first superlinear lower bound for this class, and they showed a n over log n to the 1.5 worst case lower bound for some functions deriving p. Their lower bound basically it adapts a technique of Necheporuk from 1966, and with a new structural result about comparator circuits that they exhibited. Okay, so what are our results for comparator circuits? So first, we prove the first average case lower bound for comparator circuits, which match Gao and Robert's worst case lower bound, and we also show the first circuit analysis algorithms for comparator circuits. Circuit analysis algorithms are a crucial step for understanding a circuit class, and they are well known for many of the most well-studied classes, such as AC0, ACC, De Morgan formulas, branching programs, etc. In our work, we give counting set algorithms, pseudo-random generators, and learning algorithms for comparator circuits. So first, let's talk about the average case lower bound. So average case complexity is at the foundation of cryptography. The existence of one-way functions is predicated on average case, on the existence of average case hard problems, and it's also maybe a proxy for talking about complexity in the context of more realistic inputs. So the theorem we show is that for every k, where k is at least log n, there exists a polynomial time computable function f depending on k, and which has n bits, such that for every comparator circuit C with at most n to the 1.5 gates, the circuit will agree with f in at most 1/2 plus a factor that decreases exponentially k inputs. Okay, and this can be seen to match Gauss-Robert's lower bound when we let k to be big O of log n, and the decreasing factor there in the correlation will be polynomial in n. Okay. So our next result is a satisfiability algorithm for comparator circuits. So the set problem is known to be NP complete, and it's conjectured not to have exponential time algorithms, but it still can ask the question: what about slightly non-trivial algorithms? Can we do anything better than just brute force through all inputs? This is a question that is intrinsically interesting, I think, but for the purpose of circuit complexity, it was shown to be even more interesting by Ryan Williams, who's shown that that how non-trivial satisfiability algorithms can often be used to prove circuit lower bounds for the same circuit class. Okay. So our theorem, we show that there is an algorithm that counts the number of satisfied assignments of a given comparator circuit with at most n to the 1.5 gates, taking time that is non-trivial. Okay, those numbers there are easily seen to be non-trivial when k is little omega of log n. The runtime becomes 2 to the n over a super polynomial factor. Our second algorithm is a pseudo-random generator. So a pseudo-random generator is a deterministic efficient procedure whose output looks random over uniformly random inputs for a given circuit class. In other words, the output is indistinguishable from a random input for a circuit class. In a way, it exhibits a fundamental weakness of that circuit class. And it's closely related to de-randomization and cryptography. So our theorem, we show that there is a pseudo-random generator of seed length s to the n over 2 over 3 that follows comparator circuits with s gates. Okay, so basically, if the comparator circuit has size at most n to the 1.5, then there's a pseudo-random generator that fools this comparator circuit. Using established and known techniques, this can be used to prove n to the 1.5 lower bound for MCSP against comparator circuits. And so MCSP is the minimal circuit size problem. It's a problem of deciding where a given truth table of a function, whether it can be computed by a small circuit or not. And this is a very important problem in computational complexity in itself, but a recent line of work called harness magnification has intensified this interest by showing that weak circular bounds for variants of MCSP also imply complexity breakthroughs. Okay. Yeah, so we can use our pseudo-linear generator to also prove a lower bound for MCSP against comparator circuits. So what are our techniques? We use a well-established technique called shrinkage. Under random restrictions, we show that if you randomly fix a fraction p of the values of some variables, the size of the circuit shrinks by a factor p to the gamma for some gamma. And we show that it happens with high probability. And gamma is also known as the shrinkage exponent. And shrinkage can be used to show average case lower bounds and pseudo generators. And in our work, we show how shrinkage can be used also to analyze comparator circuits, and we give a more detailed analysis to give the matching lower bounds, for instance. So the question is, how can we apply shrinkage for comparator circuits? If you think of that drawing, when you set the value of a wire, we can only eliminate one gate, right, in the worst case. Maybe if that wire is connected to only one gate. It's not clear how to apply the shrinkage technique here. However, a structural result of Gall and Robert showed that whenever a comparator circuit has L wires, there is also an equivalent comparator circuit with L wires and L choose 2 gates. This means that if we shrink the number of wires under restriction, we also indirectly shrink the number of gates. So instead of trying to prove directly a shrinkage for gates, we prove a shrinkage for wires. Okay, and this gives us a shrinkage on the size of the circuit in general. We also describe data structure for implementing Gall and Robert's conversion. In other words, given a comparator circuit with L wires, this data structure helps to find another equivalent comparator circuit with L wires and L choose 2 gates efficiently. And this is used in our satisfiability algorithm, where we store the number of satisfying assignments of all restricted circuits. So open problems. Can we improve the analysis from n to the 1.5 to n to the 1.51? This would, of course, be implied by a better shrinkage result, where gamma is at least 1/2. So is this lower bound the best possible with current techniques, or can we push the boundary further? This is strongly connected to hardness magnification. So can we show that n to 1.51 lower bounds for comparator circuits for some specific function like MCSP have major consequences in complexity theory? We can show that n to the 2.01 is enough, but this is far from the best lower bounds we know. And finally, a question that I'm personally more interested is the question about the approximation method. So the largest restricted circuit class that the approximation method of Razumov is capable of capturing is the class of non-deterministic branching programs, which are simulated by comparator circuits. So I'll be interested in knowing whether the approximation can also be used to study comparator circuits and perhaps even be used to prove lower bound for majority in this model. Thank you.